Hello and welcome. In this video, we will be exploring the vector product, also known as the cross product. This is a key topic in the IB Mathematics Analysis and Approaches higher level curriculum. By the end of this session, you will be able to define the vector product, calculate it using two different methods, understand its geometric properties, and apply it to solve problems involving area and volume. We've previously encountered the scalar product, which takes two vectors and returns a scalar. The vector product is different. It takes two vectors and returns another vector. It's important to note that the vector product is only defined for three-dimensional vectors. You cannot calculate the cross product of two-dimensional vectors. So, what is this resulting vector? The vector product of two vectors, let's call them A and B, is a vector that is perpendicular to both A and B. Let's visualize this. Imagine two vectors, A and B, lying in a plane. Their cross product, A cross B, will be a vector that points straight out of or into that plane, forming a 90-degree angle with both A and B. Let's see how we can derive the formula for this vector. Suppose we have a vector x with components x, y, and z, which is perpendicular to two other vectors, A and B. If x is perpendicular to A and B, their scalar products must be 0. This gives us two equations, A dot x equals 0 and B dot x equals 0. Expanding these dot products gives us a system of two linear equations with three variables. We can solve this system for x and y in terms of z. After some algebraic manipulation, which you can find in your textbook, we arrive at a solution. The solution shows that x, y, and z are proportional to these specific expressions. The vector a2b3 a3b2, a3b1, a1b3, a1b2, a2b1 is the simplest non-zero vector that satisfies the condition of being perpendicular to both A and B. This vector is defined as the vector product of A and B, written as A cross B. This formula is provided in your IB formula booklet, but it can be tricky to remember and apply correctly. Fortunately, there's a much more intuitive and less error-prone method for calculating the cross product, which uses determinants. Now, let's apply this to the cross product. We can express the cross product, A cross B, as the determinant of a special 3x3 matrix. The first row of this matrix consists of the standard unit vectors I, J, and K. The second row is the components of vector A, and the third row is the components of vector B. Let's expand this determinant along the first row. We get I times the determinant of the 2x2 matrix formed by covering I's row and column, minus J times its corresponding determinant, plus K times its determinant. Notice the alternating signs, plus, minus, plus. This is crucial. Calculating these 2x2 determinants gives us the exact same formula we derived earlier. This determinant method is much easier to remember and apply. Just be careful with the negative sign on the J component. Let's work through an example to solidify this method. We'll use the vectors from your notes. Let's find the cross product of vector B, which is 1, 2, 3, and vector C, which is 2, 0, 4. First, we set up our determinant matrix with I, J, K in the first row, the components of B in the second, and the components of C in the third. Next, we expand the determinant. We have I times the determinant of the 2x2 matrix, 2, 3, 0, 4. Minus J times the determinant of 1, 3, 2, 4, plus K times the determinant of 1, 2, 2, 0. Now we calculate the 2x2 determinants. For I, we have 2 times 4 minus 3 times 0, which is 8. For J, we have 1 times 4 minus 3 times 2, which is minus 2. And for K, we have 1 times 0 minus 2 times 2, which is minus 4. Simplifying this gives us 8i plus 2j minus 4k. So the vector product B cross C is the vector 8, 2 minus 4. A great way to check your work is to verify that the resulting vector is indeed perpendicular to the original vectors. We can do this using the scalar product. Let's check if 8, 2 minus 4 is perpendicular to B. Their dot product is 8 times 1 plus 2 times 2 plus minus 4 times 3, which equals 8 plus 4 minus 12, which is 0. Since the dot product is 0, they are perpendicular. Let's also check with Circa. Their dot product is 8 times 2 plus 2 times 0 plus minus 4 times 4, which is 16, plus 0 minus 16, also 0. This confirms our calculation is correct. The vector product has several important algebraic properties that are essential for solving more complex problems. Let's go through them. First, as we've established, the cross product A cross B is a vector perpendicular to both A and B. Second, the cross product of any vector with itself is the zero vector. This makes sense geometrically as two identical vectors are parallel, and the cross product of parallel vectors is 0. We'll prove this later. Third, the vector product is anticommutative. This means that A cross B is equal to the negative of B cross A. They have the same magnitude, but point in opposite directions. Fourth, the scalar triple product is a dot product involving a cross product. It's a scalar value that represents the volume of a parallel pipe defined by the three vectors. We'll explore this in more detail later. Fifth, the vector product is distributive over vector addition. This means A cross B plus C is equal to A cross B plus A cross C. And finally, this distributivity extends to the product of two sums of vectors, similar to how you would expand a binomial in algebra, but you must maintain the order of the vectors. Let's use these properties to simplify some expressions, as seen in your notes. Consider the expression A cross A plus B. Using the distributive property, we can expand this to A cross A plus A cross B. We know that the cross product of a vector with itself is the zero vector, so across A is 0. This simplifies the entire expression to just across B. This is a very useful simplification. Let's try another one. How about the scalar triple product 2A dot A cross B? We can pull the scalar 2 out of the dot product. This gives us 2 times the scalar triple product A dot A cross B. Now let's think about the term inside the parentheses. We know that A cross B is a vector perpendicular to A. Therefore, the dot product of A with a cross B must be 0. The dot product of two perpendicular vectors is always 0. So the entire expression simplifies to 2 times 0, which is just 0. This is another powerful result. A common application of the cross product is finding a vector perpendicular to a plane. If you have 3 points in space, they define a plane. To find a vector perpendicular to this plane, we can first form two vectors that lie within the plane. For example, if we have points A, B, and C, we can form the vectors A, B, and AC. Since both A, B, and AC lie in the plane, their cross product, AB cross AC, will be a vector perpendicular to both of them, and therefore perpendicular to the plane itself. Let's work through an example from your notes. We need to find a vector perpendicular to the plane containing points A, 1, minus 1, 2, B, 3, 1, 0, and C, minus 1, 2, minus 3. First, we find the vectors A, B, and AC. AB is B minus A, which is 2, 2, minus 2. AC is C minus A, which is minus 2, 3, minus 5. Now, we calculate their cross product. We set up the determinant with I, J, K, the components of AB, and the components of AC. Expanding the determinant gives us I times minus 10 minus 6, minus J times minus 10 minus 4, plus K times 6 minus 4. This simplifies to minus 4I plus 14J plus 10K. This vector is perpendicular to the plane. Any non-zero scalar multiple of this vector, like 2 minus 7 minus 5, would also be perpendicular to the plane. We've seen how to calculate the cross product and that it's perpendicular to the original vectors. But what is its direction? The direction is determined by the right-hand rule. If you point the fingers of your right hand in the direction of the first vector, A, and then curl them towards the second vector, B, your thumb will point in the direction of the cross product, A cross B. This rule explains why the cross product is anticommutative. If you curl your fingers from B to A, your thumb will point in the opposite direction. Let's apply this to the standard unit vectors, I cross J. Point your fingers along the x-axis I and curl them towards the y-axis j. Your thumb points up the z-axis, which is the direction of k. So I cross j equals k. Now j cross I. Point your fingers along the y-axis j and curl them towards the x-axis I. Your thumb points down the z-axis, which is the direction of negative k. So j cross I equals negative k. This confirms that j cross I is the negative of I cross j. Now let's discuss the magnitude, or length, of the cross product. The formula for the magnitude is given by the square root of the sum of the squares of its components. This is the standard formula for the magnitude of any vector. However, there is a much more useful geometric formula. The magnitude of A cross B is equal to the magnitude of A times the magnitude of B times the sine of the angle theta between them. This formula is incredibly powerful. Let's look at the immediate consequences of this formula. First, if A and B are non-zero vectors, their cross product is the zero vector if and only if they are parallel. This is because if they are parallel, the angle theta between them is 0, or 180 degrees, and the sine of both of these angles is 0. Second, if A and B are perpendicular, the angle theta is 90 degrees, and sine of 90 is 1. In this case, the magnitude of their cross product is simply the product of their magnitudes. Let's verify this with an example from your notes. Let's take the vectors p equals 2, 1, minus 5, and q equals 3, minus 1, 1. First, let's check if they are perpendicular by calculating their dot product. P dot q is 2 times 3 plus 1 times minus 1 plus minus 5 times 1, which is 6 minus 1 minus 5, which equals 0. So P and Q are indeed perpendicular. Now let's find their cross product. Using the determinant method, we get the vector 4 minus 17 minus 5. Let's calculate the magnitude of this cross product. It's the square root of 16 plus 289 plus 25, which is the square root of 330. Now let's calculate the product of the magnitudes of P and Q. The magnitude of P is the square root of 30, and the magnitude of Q is the square root of 11. Their product is the square root of 330. The magnitudes are equal, which verifies our formula for perpendicular vectors. The geometric formula for the magnitude of the cross product, across B equals theta, has a very important application, finding the area of a parallelogram or a triangle. Consider a parallelogram defined by two adjacent vectors, A and B. The area of this parallelogram is given by the magnitude of their cross product, A cross B. This is because the area of a parallelogram is base times height. The base is the magnitude of B, and the height is the magnitude of A times sine of theta. This is exactly the formula for the magnitude of the cross product. Since a triangle is half of a parallelogram, the area of a triangle defined by two vectors A and B is half the magnitude of their cross product. Let's find the area of a triangle given its vertices. We want to find the area of the triangle with vertices A, 2, 1, 1, B, 4, 3, 0, and C, 1, 3, minus 2. First, we need two vectors that form two sides of the triangle. Let's use A, B, and AC. AB is B minus A, which is 2, 2, minus 1. AC is C minus A, which is minus 1, 2, minus 3. Next, we calculate their cross product. AB cross AC is the determinant of the matrix with I, J, K, the components of AB, and the components of AC. Expanding this determinant gives us the vector minus 4, 7, 6. Finally, the area of the triangle is half the magnitude of this vector. The magnitude is the square root of 16 plus 49 plus 36, which is the square root of 101. So the area is 1/2 times the square root of 101 square units. The scalar triple product A dot B cross C also has a significant geometric interpretation. It represents the volume of a parallelepiped. A parallelepiped is a three-dimensional figure with 6 faces that are parallelograms. If it is defined by three vectors A, B, and C originating from the same vertex, its volume is the absolute value of the scalar triple product. Let's understand why. The area of the base of the parallelepiped, which is a parallelogram formed by B and C, is B cross C. The height of the parallelepiped is the component of vector A that is perpendicular to the base. This height is given by the magnitude of A times the cosine of the angle between A and the normal to the base, which is B cross C. The volume is then the base area times the height, which simplifies to the absolute value of A dot B cross C. A tetrahedron, or triangular base pyramid, is 1/6 of a parallelepiped. Therefore, its volume is 1/6 of the absolute value of the scalar triple product. This formula is also very useful for finding the volume of a tetrahedron given its vertices. Let's find the volume of a parallelepiped. We have a parallelepiped with vertices at the origin O, 0, 0, 0, and adjacent vertices A, 3, 0, 0, B, 0, 1, 0, and C, 1, 2, 3. The defining vectors are the position vectors of A, B, and C, so A is 3, 0, 0, B is 0, 1, 0, and C is 1, 2, 3. The volume is the absolute value of A dot B cross C. We can calculate this using a determinant. The volume is the absolute value of the determinant, with rows A, B, and C. Expanding this determinant along the first row, we get 3 times the determinant of 1, 0, 2, 3, which is 3. The other terms are 0. So the volume is the absolute value of 3 times 3, which is 9 cubic units. Let's recap what we've learned. We've defined the vector product, learned how to calculate it using the determinant method, and explored its key properties. We've seen that the cross product of two vectors is a vector perpendicular to both, with its direction given by the right-hand rule. Its magnitude is sin theta, which allows us to calculate the area of a parallelogram or a triangle. Finally, the scalar triple product gives us the volume of a parallelepiped, or a tetrahedron. To help you master these concepts for your IB exams, here are 5 practice questions. Pause the video, work through them, and then resume to see the fully worked solutions. Here are the questions. They cover calculation, properties, and geometric applications. Welcome back. Let's go through the solutions. For question 1, we calculate the cross product using the determinant method. The result is I plus 5j plus k. For question 2, we need to find A dot A cross B. We know that A cross B is a vector perpendicular to A. Therefore, their dot product must be 0, no calculation is needed. For question 3, we find two vectors forming sides of the triangle, PQ and PR. Their cross product is -1, 1, 10. The area is half the magnitude of this vector, which is 1/2 times the square root of 102. For question 4, we first find a vector perpendicular to U and V by calculating their cross product, which is 3, 1, 1. We then find the unit vector in this direction. Finally, we multiply this unit vector by 3 to get two vectors of length 3, 1 in each direction. For question 5, we find the 3 vectors from the origin to the other vertices. We then calculate the scalar triple product, which is 15. The volume of the tetrahedron is 1/6 of this, which is 2.5 cubic units. Finally, let's discuss a statement from your notes. Scalar product is a measure of the parallelism of two vectors, whereas vector product is a measure of the perpendicularity of two vectors. This is a great way to summarize the difference between the two products. The scalar product, A dot B equals theta, is maximized when the vectors are parallel. Theta equals 0, cos theta equals 1, and is 0 when they are perpendicular. Theta equals 90, cos theta equals 0. So a large scalar product means the vectors are close to parallel, and a zero scalar product means they are perpendicular. The vector product, across B equals sine theta, is 0 when the vectors are parallel. Theta equals 0, or 180, sine theta equals 0, and is maximized when they are perpendicular. Theta equals 90, sine theta equals 1. So a large magnitude of the cross product means the vectors are close to perpendicular, and a zero cross product means they are parallel. This distinction is fundamental to understanding how and when to use each product. The scalar product is for angles and projections, while the vector product is for perpendicularity, areas, and volumes. Thank you for watching. I hope this video has provided a clear and rigorous explanation of the vector product, its properties, and its applications, preparing you for your IB exams.